All right, let's talk about the regression model. We want to think of the ith response as a random variable that depends on on the independent variable, on the ith observation of the independent variable, which we'll call x. Okay, we typically use capital letters for random variables and little lowercase letters for their deterministic counterparts, but in general, sometimes we'll want to think of the independent variable or the explanatory variable as something that is also random. But for now, and for a lot of what we do, we'll want to think of this as something that we can control. So this will oftentimes be, you might think of it as a little x, but nonetheless, we'll still use big X here from time to time. All right, so here's the idea. You might think of this as your x-axis is, there's some knobby over here. You can turn this knob, and by turning this knob, counterclockwise or clockwise, this thing will have some sort of an effect on the response. Maybe if you turn it clockwise, as you turn it clockwise, the response tends to go up. Okay, something like that. Now, so the idea is our regression model we think of as maybe it's some sort of a straight line, and so the response should be linear in the independent variable, or in the explanatory variable, or in the predictor variable. Okay, so we want to model this as some slope, some actual slope times whatever x value. Let's say here's the x, the ith x value. Then the y value here we'll think of as a random variable that hits around this line. Okay, the equation of this line is b naught, or beta naught, sorry, plus beta 1 times xi, and then plus some random error term. Okay, that is maybe on the average this is where your response is, right there on the red line, but we'll think of the idea here is that the response has some distribution that's conditionally dependent on the value of the x variable. Okay, what I've drawn here, it looks like a nose, but it's really, hey, look at that, it's like a normal density function just turned over on its side, just to kind of indicate that sort of on the average the observations will tend to cluster around the values on the red line. Similarly, if I'd had maybe the jth observation value, or the jth x setting is down here, or something like this, then you can think of the response down here might also be sort of normally distributed, but with mean there. Okay, and similarly, up here. Okay. So this is sort of a good picture to get in your head. There's a good picture in your textbook that sort of looks like this, and that is that the response values sort of tend to sort of cluster in and around that point. Okay, and the response values when x is here tend to sort of cluster in and around there, occasionally far off. Okay, something like that. So the beta naught and the beta 1 are the actual intercept and slope parameters you'd find if you could use all the possible observations, and we estimate them with b0 and b1 from those previous equations. That is, b naught you can think of as an estimator, is an estimate for beta naught, and b1 is an estimate for the actual slope. Okay. These error terms we will assume to be independent. We'll also assume that the expected value of each error term is 0, and the variance is constant, is some sigma squared, which we don't know for sure, but that it is constant across all independent variable values. Okay. Okay, so here's some facts about our model, sort of a summary of the facts about our model here. We want to think of these error terms, these random errors, these epsilon i's, as independent random variables with mean zero and common variance sigma squared. And for now, and in much of our study of regression, we'll also assume that they're normally distributed. Hence the reason why I drew those curves like that. Okay, so that means so that the full response then is a linear function of just the xi's, but also plus this normal error term. That's just the epsilons are we'll assume are independent. They all have the same variance. That's why I sort of attempted to draw these normal curves to be exactly the same, just shifted by going up, as you go up the line there. Okay. All right. So I really should have drawn that picture down here, but so that's the idea. Okay. That's the idea. That's what number one is all about. Sort of. Okay. The mean response, or the expected response at each value of predictor xi, is a linear function in the xi. In fact, so if I do something like this, I say put a vertical line there. Okay, what this means is this line, you should have seen if you've studied conditional probability all in a first statistics course. This line means given. Okay, so this is really conditional expectation. It's the idea is here we're trying to get an expression for the expected value of the ith response given that the ith value of the independent variable takes on the value of x. So if x takes on a value, say right here, if xi equals x, then the expected value of yi turns out is right there. This is due to the fact that this will be the expected value of, if I substitute this stuff down into there, okay, then I get it's the expected value of beta naught plus beta 1 xi plus epsilon I given xi equals x. Well, if xi equals x, then I can just replace the xi with x, okay? And this is the expected value of what? Beta naught plus beta 1 times little x plus epsilon I. And so this is just the expected value of a sum is the sum of the expected values, it turns out. And beta naught is a number. We might not know it, but it's just a number. And these are just numbers, b1x. The only random thing there is the epsilon I. And what is the expected value of epsilon I? It's 0. So the idea here is that in fact, yes, if we stipulate that our independent variable value is fixed at x, then we want that the expected value of our response hits right at that line. Okay? That's exactly what that says. That the expected value of the response is beta naught plus beta 1 times x. Now, it turns out that the Gauss-Markov theorem, this famous theorem, you can find this in your book, says that the estimators given in those previous expressions that we use are unbiased, meaning that on the average they actually hit where they're supposed to, okay? So that they're unbiased, and they have the minimum variance among all unbiased estimators. So this is good. It turns out, you'll see in the homework, that there's often several types of ways to estimate quantities, and some of them are better than others. There are lots of attributes that make estimators attractive. We like estimators with small variance because it means that they're sort of very predictable, okay? We like small variation in our estimators. And finally, this point number 4, just want to make this clear again. At some point, we will relax the normality assumption on these epsilon i's. Okay, we won't always assume that these that the responses are normally distributed for a fixed x value. And also, at some point, we will likely allow these xi's to be random and not just something that we can control, like with a knobby. Okay, that maybe that the explanatory variables are also random.